All right, so now that we've talked about some of the different types of characteristic X-rays, I want to compare some of their characters, some of their properties. And so to do that, though, we need to define a term, and that is the fluorescent yield. So this is used to measure the relative effectiveness of X-ray generation. So basically the ratio of photons produced by the ionization. So basically the idea here is if you bombard a material and therefore produced characteristic X-rays, which ones will be more bountiful than others? And so that's what we're going to look at here. So let me switch and show you the slide comparing the K, L, and M series with the fluorescent yield. Okay, so if you take a look at the graph on the left, again, you'll see this term fluorescent yield. So that is how much the ratio of photons produced when you're talking about the ionization. And so we have the K, L, and M series, and it's as a function of the atomic weight. So which ones will be produced given a certain atomic weight or atomic number. So what we see here, just general trends, is that everywhere, if we pick any sort of atomic number, the K is always has more fluorescent yield than the L, which has more than the M. So we're going to expect to generate the most K shell characteristic X-rays. Those are going to be the most plentiful, and then the L, and then the M. And the amounts that we see of the others go up, or sorry, the amounts of everything go up with increasing atomic number. So if we're up here and, for example, the 60, right, we see a lot more L than we did down here at 30 or 40. And then the K tends to plateau off at the very high atomic numbers. But this basically just tells us that the yield increases with increasing atomic number, and the K series is more effective than the L, which is more effective than the M. So we expect to see those and more than the others. So this table over here, table 6.2 in our book, gives the same kind of information that the graph does. And so it just gives us their fluorescent yield for different elements with their atomic number. And so we see that obviously since the K shell represents n equal 1, not all elements will have the n equal 2, which would be the L shell. And so that's why you don't see L or M on some of the early elements, and then you do later on. So if we look at this, the other thing we notice is that on these very low elements, and you'll actually notice that it only starts at 4 here, the yield is 0 for lower than 4, right? So we don't really expect to get even K electron or K characteristic X-rays for really light elements such as beryllium or lighter, so hydrogen, helium, and lithium. So this is a big issue if we think about something like lithium-ion batteries, right? Lithium is the third element, and it has a very low, if basically 0, fluorescent yield, and so we don't even expect to see those. And so we can't use these techniques, these X-ray spectroscopy techniques, to use lithium in these ways since the amounts are so low. And really, if we get all the way up to oxygen, the yield is very low for those, so quantification can be difficult. So along with this, along with the fluorescent yield, the energies of these follow the same order as well. And so if I go to the next slide, we can see that the characteristic X-ray wavelengths and also energies. So I've got lambda for the wavelength and E for the energy. And basically we see the same trend, is that if we go up in atomic number, the energy goes up, and therefore the wavelength follows the reverse trend, and so the wavelength goes down. And you can see the same types of trends that we have there. Okay, so this is what we these are the values that we see. And when we're looking at something like energy dispersive spectroscopy, typically when we do this in the electron microscope or externally, we take a spectrum of results from 0 up to a certain energy level. And so that energy level that we go up to dictates what we end up seeing. So this, you start out, very low, and then we go all the way up. And you can see some of these other energy values. And this kind of determines what we see in those cases, because our energies start out small, and then same thing with the L shell. We see that those energies also increase. So basically, the K lines that we see tend to be missing in the heavier elements. So if we look down here, and something like platinum has an energy value of 66 because its number is so high. And so if our typical spectrum is run from 0 to, say, 20 kiloelectron volts, then we wouldn't expect to see the K shell for platinum, whereas the other two, their energies are lower, and so we would expect to see the L and the M shell because their energies are much lower than the K shell. So because of that trend, we don't see the K shell. So that gives us a lot of things to think about when we think of the spectrum for something like EDS. Okay, so based on these values that we see in this table 6.3, so again, this is in your textbook if you need to see more of this. I've just got a snapshot of it here. What I want you to do is a question on the quiz, and that is suggest what the energy scan range should be if we want to detect the K series for the first element, which is cerium. So think about finding cerium. And what range would you need to scan to, say, see the K series for cerium? And then secondly, what would you need to do to see the K series for platinum? So answer that. We'll come back and talk about the solutions. Okay, so we're back. So let's take a look. So first of all, cerium. And so this is 58 cerium. And you see this first column here is for wavelength. So the second one, this is the energy for the K series. So it's 34.62 or 72. So we would have to scan at least up to that value. So around 35 keV of energy to enable to get that. And oftentimes you have to scan a little bit higher. So something right at the borderline sometimes isn't captured very well. So even probably higher than 35 keV, but at least that level. Same thing if we go to platinum, 78, we see that energy is 66.83. So we probably have to go up to at least 67, if not higher. So that is really high. But the useful thing is we don't typically do that for EDS scans. What we do is we rely on the others. So we rely on the L, or we rely on the M, which have much lower values. So around 10 keV and 2. And if we go back up to cerium, 2.5. Around 5 and around 1. So on a typical scan from 0 to 20 keV, we would see the L and M for those heavier elements. And so we don't have to scan up to the really high ranges in order to capture the K series. That's just a hypothetical. Okay, so this table has lots of values for energy and wavelength values. And so you can also, if there's anything missing, you can also find tables like this readily available on the internet and other references as well.